Hello everyone, and welcome to a video where we are going to be solving the 2021 external exam for specialists. So basically working through the short response tech-free part of the paper. I might do the multiple choice in another video, although normally the multiple choice can be a little bit easier to figure out. Of course, our short response has both our complex familiar and our complex unfamiliar questions. Now listen, I feel like I need to just get this, out the way early on. My wife's insisted I grow a mustache. I don't know how I feel about it. Yeah, it's happened. It has happened. But listen, despite my appearance and this new thing, the maths side of things, that hasn't changed since 2021. Clearly, this is the 2021 external exam. So, let's jump into it. We should be able to solve the first few questions relatively simply because these are our simple familiar questions. When we're preparing for our external exam, we should be coming in with a decent amount of confidence around how we can actually go about solving our simple familiar questions. If you're trying to get high marks, we really want to be getting close to 60% out of the 60% simple familiar marks. Of course, that 60% does include the multiple choice question options. So, with that being said, right, we're pretty much trying to nail the multiple choice plus the first, up to question 15, 16 from your short response. So, question 11, and normally these earlier questions in the paper are essentially just skill checking you, right? Like, do you know the basic foundational skills? Normally how these papers work is simple familiar questions and normally assessing one, maybe two skills. They could either be one sort of more involved skill or it can be two small skills. This first question, right, is worth 1 mark. So we're expecting 1 mark. We're assessing one skill. This is a real basic function notation question. We want to let f of x equal tan to the negative 1 or arctan brackets x over 2. And we want to do that between my domain of negative pi on 2 to pi on 2. I want to determine f of 2. Well, this is simply just substituting 2 in place of x into my expression. That means I get tan to the negative 1 of 2 over 2. And this is really just testing our knowledge on exact value triangles. This is a question which should have a very high success rate in terms of answers. I simply get tan to the minus 1 equal to 1. I can consider my domains here a little bit. My domains for, how many values should I be looking for, right? Obviously, in this particular situation, tan has 2 values between 0 to 2 pi. That's going to give an answer of 1. This is from minus pi on 2 to pi on 2. If we struggle to visualize these things, I strongly recommend drawing a graph, okay? Negative pi on 2 is down here. Pi on 2 is down here. So we're really just looking at specifically quadrants 1 and quadrants 4. Meaning I'm only needing to consider one of my possible solutions, well, tan of pi on 4 or 45 degrees if you prefer to work in degrees. In other words, it's going to be here, right? Pi on 4 here. That is going to be my answer for tan to the negative 1 brackets of 1. Okay, this is basically saying what angle gives an exact value of 1. That angle is going to be pi on 4. So, some quick skill checking to begin. We got a part B and now it says, okay, we got this part. Let's differentiate and we'll put 2 in again and we'll see if that changes the question. Again, this is essentially testing us on our foundation knowledge of do we understand what an inverse trig function is. We can actually look at our formula sheet here. We can get the formula for how we differentiate an inverse, an inverse trig function. How we differentiate an inverse trig function, how we differentiate tan to the minus 1. Normally, we get this idea here, right? Where if I've got tan to the minus 1, maybe I should rewrite the formula out, right? I don't have my formula sheet on me, but it should be something like this. If I differentiate with respect to x, tan to the negative 1 of... Okay, so it is exactly as it basically looks above, right? We get simply just x over a. Tan to the minus 1 of x over a is equal to a over a squared plus x squared. That is essentially how our formula sheet functions for this particular question. So again, look at our formula sheet. We get our values. Now I simply just apply that to my problem. Well, a is going to be 2 in this case. If I see my derivative or my function is tan to the minus 1 of x over 2. So if a is 2, I simply get an answer for f dash of x is equal to 2 over 2 squared, which gives 4 plus x squared. I can now substitute 2 into my expression, and I wind up with 2 over 4 plus 4 in this case. That's going to be 2 over 8, which gives 1 over 4. So my answer is going to be a quarter for f dash of 2. Okay, so again, just testing us on our simple familiar skills. Can we interpret our formula sheet? Do we know a little bit about our inverse tangent functions? We now want to use our results from question 11a and 11b to determine the equation of the tangent to the graph y equals f of x at x equals 2. In other words, I want to find the equation, a straight line, a tangent is a straight line. I want to find a straight line equation or a linear function at the point x equals 2, and luckily we've already gathered almost all the information we need from the first parts, from part A and part B. In part B, we found the gradient, right? If I differentiate something and I substitute in an x value, I find the gradient at that point. So now the gradient at x equals 2, which is part of the question here, the gradient at x equals 2 is going to be 1/4. So I know my gradient, and I also know the y coordinate. When x equals 2, my y coordinate equals pi on 4. So I have a coordinate point, I have a gradient, I can now go ahead and find my equation for a straight line. If I come down, I get... Well, I guess I got y equals mx plus c. So let's just start with that. We'll do y equals mx plus c. And we'll just state some of our information. I know that m equals 1/4. This is from part B. I also know that my coordinate point is going to be, that's going to be 2, and it's going to be pi on 4. This is from part A. So part B gives me the gradient, part A gives me the coordinate point I'm using. Now I can simply just put all this information into my equation for a straight line, into my y equals mx plus c, and I get y equals 1/4 multiplied by x plus c. I can now substitute in my coordinate point of 2 and pi on 4 in place of x and y. There's many ways to find the equation of a linear function. If you do it differently with the y minus y1 formula, equals m outside of x minus x1, use that, you get the same answer. I just like doing it this way. One formula to remember, y equals x plus c. So I just think it's less things to think about, less things to worry about. I'm now going to put pi on 4 in place of y and 2 in place of x, and I wind up with pi on 4 equal to 1/4 multiplied by 2 plus c. And if I kind of collect all my like terms here, I wind up simply with pi equals 1/2 plus c. I'm going to subtract 1/2 of each side. I get c equals pi on 4 minus 1/2. I can now do a few little tricks with making giving myself a common denominator, right? I can see that if I didn't simplify this to 1/2 is the same thing as 2/4. So I'm going to multiply the top by 2 and the bottom by 2. Right, essentially I'm multiplying by 1, right? 2/2 is 1, so I'm not changing the question. I'm just making sure my denominator for my fraction, the 1/2, is going to be 2/4 instead of 1/2. So I have a common denominator, so I can get a nicer-ish looking answer for C being pi minus 2 all over 4. A nice little common denominator there. If I put all that back in, I get my final equation. I'm just going to write it here because I'm running out of space a little bit, of y equals 1/4 x plus pi minus 2/4. We could make this a general formula pretty easy with this common denominator stuff. We're just going to stop. It didn't ask for anything special. We've got to our answer. Again, it's a time-based assessment. With more time, we can make everything look really pretty. But again, we don't need to, right? This is simply just a 2-mark question. We've more than satisfied what the mark scheme would have, I believe. And don't highlight your answer, right? Even if we write this kind of like crazy layout, right? You can do a little arrow if you like. Don't highlight your answer. Your exam booklets get scanned. If you highlight it, there's a chance it just reflects. The whole thing goes black, okay? Number 1 exam tip. Don't highlight answers, or you might end up submitting no answers for your external exam. That is true for every state. Do not highlight your answers. Do not use whiteout. All these things create weird issues when it comes to photocopying, or can create a weird issue when it comes to photocopying. So just to draw an arrow, it looks a little bit messy. It's fine. The people marking your exam are clever. They should be able to figure out where your answer is going to be. And it's the right answer in this case, so we're fine. We go across to question 12. Question 12 is a vector question. I get so many questions about vectors. It is a topic that gives a lot of students quite a lot of stress. So I feel like it's always good to get a vector question that's in the simple familiar category for one, right? This, again, we're just testing basic skills. It's simple familiar. So we should be able to get our answers out relatively quickly. We want to determine a normal vector n that is perpendicular to the plane. Again, this is just, do we understand how vectors work? Our normal vector is given by the coefficients of x, y, and z. In other words, my coefficients of x, y, and z are going to be 1, minus 1, and I've got minus 2 there. So my normal vector n, I'm going to write this as a column vector, is simply just equal to 1, -1, and -2. Again, it is just the coefficients of x, y, and z. And if we need more explanation than that, feel free to comment down below. But that should be something that I'm going to assume most of us have at least seen at the time we're studying for our externals. We want to determine the vector equation of a line L that is perpendicular to the plane and, importantly, contains this very specific point. Okay, so again, like a lot of these early questions, if we understand the basics, we should be able to score well. It's a 1 mark question. It's not requiring a whole lot. We should know that the vector equation of a line is very similar to y equals mx plus c. It's r equals a. That's my point, right? That's my point on the plane, which is going to be mirrored with a in the question, capital A in the question, plus t d. I put these little squiggly lines under my vectors. D is kind of like the direction of the line in three-dimensional space, or you can think of it as like the gradient, right? Sometimes you might see this equation rewritten. It's very similar to y equals like c plus xm, which is a weird way to write a straight line equation, but your y-intercept is essentially your a point, any point on the line. Your m is your gradient, that's kind of given by d, and your x and your t, you can see these are above each other. These just stay as simply just being variables. So if we understand how to find the vector equation of a line, we have a point. I know the direction, because it has to be perpendicular to the plane. We found that out in part A. Again, when we have a part A, part B, part C, normally we are required to use some of the skills we found before. So if I put A in place of lowercase a in this case, I get a vector equation of r equals -2, 1, 3, plus t outside of my normal vector, 1, -1, and -2. Now, it didn't require us to do anything else other than that. If we understand how to write it with column vectors, that's great. We could do I, J's, and K's. That's fine as well, but that's my answer. They're the numbers we care about, right? The coefficients of our I, J, and our K. So, part C. Part C wants us to use part B. So, there we go. I want to use my results from 12B to express the equation of a line L in parametric form. A good tip as well for exams is, even if you got part B wrong, it said use your results from part B. So you need to use your results from part B. You will get all the marks if you use those results correctly. So you can mess up on your equation for your line perpendicular, but you use it correctly and we're fine in the eyes of the examiner. You can still get the full 1 mark awarded in part C. So part C, parametric equations, that is requiring us to essentially write out the coefficients of my I in terms of x, coefficients of j is going to be y equals, coefficients of k is going to be z equals. So we can do things to my equation above. It depends how confident you are with reading equations based on column vectors. I'm a teacher, so, if we don't know where, I'm a maths teacher, so I'm pretty confident with how we could do something like this. So for me, it's not too difficult to look at my I coefficients are going to be the numbers on the top, okay? So I've got -2 and I've got 1. Now this 1 is going to be multiplied by t. T is going to multiply into this bracket. So my x coefficients, in this case, x is going to be equal to, I've got -2, that's my I component from the first bit, plus, because it's plus t times +1, plus 1 lot of t, or simply just plus t. Now, if you're not sure where I get those from, I'd recommend put this into I, J, and K form, collect all your like terms, right? So you just have 1I, 1J, 1K. We're just using the coefficients, but we can do it without expanding if you're confident and you've practiced it. And I'm kind of explaining, I guess, how I think of it relatively quickly. My J's are going to be the 1 and the -1. Again, t is going to multiply m. So I'm going to wind up with my coefficient for y equal to 1. It's t times -1, so it's going to become -t. And then my coefficient of z is the same idea. It's going to be 3 minus 2t. So pretty easy. It's 1 mark. We should be able to get that with expanding or by looking at my column vectors and just doing a little bit of mental gymnastics to get to our solutions. Part D is 3 marks. So 3 times as hard. Not really how the mark scheme works. Some people do think that's how the mark scheme works. It doesn't work that way. But we are going to have to demonstrate more than just basic skills. A 1 mark question is basically answer, done. A 3 mark question is justify how we get to an answer, show some working out. So if you read the question, it says the line L and the plane intersect at point S. Show that the coordinates of S are 2, -3, and -5. So these show questions, this is where the external exam can challenge people, is there is so many little wrinkles that can get asked. This isn't something that you've probably practiced a ton. Maybe it is, in which case you've done a great job studying and covering all your bases, but it's probably not something you've studied a ton. You might have done this a few times leading up to maybe IA2, but like bigger picture, maybe you haven't done a ton of work on showing what the coordinate points are. So when we're trying to demonstrate coordinate points, what we actually want to do is we want to take our x, our y, and our z. We want to put that, this is part of part C, right? Using our part C, our x, y, and z from part C. Okay, we are going to put, I'll use yellow, we're going to put these, maybe I'll change my colors up, we'll do yellow, green, and blue just to help emphasize the point. We're going to put these solutions, these values for x, y, and z, we're going to put these back into my original equation. I'm going to put my x in place of x, my y in place of y, and my z in place of z. And it's also going to equal 15. So we're just going to do a substitution. We're going to substitute in, and we're going to try to find the time when everything basically, when they intersect. We're going to basically find the intersection point. We do that by using substitution. So what I wind up with is, and I'll zoom out hopefully so we can see everything that I'm doing all at once. We have 1 times, I'll just put it like this, just to really make sure we understand what's going on, right? We should multiply by our coefficients. That is going to be minus, is going to be minus 1 minus t, and it's going to be minus 2 outside of 3 minus 2t. All of that is still equal to 15. I'm just going to make sure that I'm 100% correct. And you can see it is 1 minus 1 and it is minus 2. So this is my equation of a line. Okay, now 1 second, my phone is ringing. My phone is no longer ringing. So let's hope. I thought there was something important. Maybe not. We'll see if they leave a voicemail, but I'll worry about that later on. Apologies for the delay. So now I expand each bracket. I'm going to collect like terms. I'm going to solve for t. So I expand each bracket. Well, it's 1, so it's going to stay the same, right? The first bit's just simply going to be minus 2 plus t. I am putting a negative 1 in, right? I can put my little negative 1 there. I just put a minus out the front, but I can put a negative 1 there if that helps you guys see what we're meant to do. And I get minus 1 plus t. Negative 2 times 3 gives negative 6 plus 4t, all equal to 15. I collect my t's together. I get t plus 4t. That is going to give me 6t. And I've got minus 2 minus 1 gives minus 3. Minus 6 is going to give minus 9, all equal to 15. I can add 9 to both sides. If I add 9 to both sides, I get 24. So I get 6t equal to 24. I get an answer for t of simply just 4. I know the time where they intersect is at 4 seconds. I can now substitute that back in place of my x, y, and z, again, essentially using these parametric equations from above, and I can show that, well, x should equal 2, because these two things should line up. X should equal 2, y should equal minus 3, and z should equal minus 5. If I substitute t equals 4, I'll write here, if I basically substitute t equals 4 into all 3 of these equations. And I'm pretty confident the answer is going to turn out right. I can actually look at them, and this is like, you can mental math this too, right? But I'm going to just show it properly. So I'm going to get my little lasso out. You can't do this in the exam, obviously, but also you may not need to write so big. So hopefully that'll fix it. I'm going to shrink this down just a little bit. My dots have gone. Okay, well, hopefully we're following me, understand what's happening. I'm now going to put t in, and I get, we can write this a few different ways, right? I'm going to show it's a coordinate point. I can write my coordinate points as x, y, z. So I'm going to say, okay, x is equal to minus 2. T's 4, right? Minus 2 plus 4. Y is equal to 1 minus 4. And z is equal to 3 minus 2 times 4. And all of that is going to equal, well, minus 2 plus 4 is going to give 2. 1 minus 4 gives minus 3. And 3 minus 8 is going to give negative 5. So therefore, I have proven, I'll put my little therefore dots. Therefore, I have proven that the point of intersection is when t equals 4. And all those points line up to 2, minus 3, and minus 5. Oh, okay, so if you did write that big, I didn't need to shrink it. I actually had space here. So I could have just turned the page. Obviously, you're going to have reading time, and you're going to read through. I haven't really read through this properly, right? But in your exam, you'd have reading time. You would read through. And you would see, maybe you remember that you have extra space for part D. So, we're still going though. I want to determine AS. I want to determine the vector from A to S. The way I normally do this is final minus initial. We just found point S from before. I guess this is why they made it a show, right? So you could still do part E, even if you didn't have, even if you didn't find the answer, because you know S is 2 minus 3 minus 5. So I do final minus initial, okay? Therefore, my point AS, A to S, is equal to, essentially, it is S, which is the column vector we just found. That is it all negatives? Oh no, it's just 2 minus 3 minus 5. That is 2 minus 3 and minus 5. Sorry, that's a weird minus 3. Let me fix that up. Can't do that part in the exam, apologies. But yeah, I can, so why not? And then part A, all the way from before, part A is going to be here, given in part B, that is minus 2, 1, 3. So even if you couldn't do any of the bits right, you still could have got full marks on E, because you had all the information just given to you in the question. It is negative 2, 1, and 3. So I'm going to do this. It is negative 2, 1, and 3. I simply just subtract these 2 points. 2 minus minus 2 is going to give plus, so it's going to become 4. Minus 3 minus 1 is going to give minus 4, and minus 5 minus 3 is going to give negative 8. Now, we might notice there's a common factor here. When we see common factors, well, how many marks is this? It's 1 mark. We probably don't need to do it for all the marks, but it's just such good habits, right? If we're watching this video, we're studying for the external. What are some good habits I should keep in mind? See a common factor, take out a common factor. You're never going to be wrong for taking out common factors. You could be wrong for not taking out common factors. So we're going to take out the common factor of 4 here. I take 4 out the front, and I get 1 minus 2, and... Wait, that's wrong. That's wrong. My brain was like, I said the wrong number there. 1 minus 1 and minus 2. Minus 2 is an answer. It's just the Z coordinate, not the Y coordinate. So I've got my J coefficient, K coefficient. You guys get what I mean? So I've got my vector AS. Part F. Use a property of parallel vectors to justify that AS is parallel to the normal vector from before. Okay, 1 minus 2 and minus 2. 1 minus 2 and minus 2. By taking out a common factor, I've essentially done it, right? We'll formalize this a little bit. For parallel vectors, if we aren't aware of a parallel vector, we can say that a vector is parallel. What's the best way to write this? I'm just going to do it like this. We'd say A is parallel to B if we get this situation here, where K is some kind of scalar quantity. There's different ways to write this. This is the easiest way for me to remember it. So you can see that my K value in this case is 4. Otherwise, the vector is the same. The direction for a vector, if we don't know, the direction for a vector comes from the ratios between your I, J, and K components. So essentially, like, you know, how far across, up, down, like in 3 dimensions. So if that ratio is the same, you can see it's 1 minus 1 minus 2. If I put the 4 in and I get 4 minus 4 and minus 8, it's still the same ratio. So because the ratio is the same, therefore they're parallel. I just got a scalar quantity out the front. So I'm going to say that my normal vector is equal to 4... Whoops. Did my pen run out? There's no way my pen just ran out. Tip tap, tip tap. Oh, my pen didn't run out. Okay, cool. Do you know what happened? So it's going to be basically 4 times vector AS. Okay, it's... other way around. Wait, sorry, other way around. AS is 4 times vector N. Yes, AS is 4 times vector N. Sorry, my brain took a little bit of buffering there. There we go. There we go. Yes. 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 AS equals 4 times vector N. Yeah, we're happy. KB. Yep, it's cool. Nice. Done. I could have done it the other way around. I could have done vector N equals a quarter AS, but it's fine. We're fine. Okay, it all works. It all works. So, that's done. 1 mark, done. Okay. Maybe I could write therefore vectors are parallel, but it's 1 mark. I think I'm okay. Complex numbers, eh? Complex numbers. So, this is interesting. Okay, so, for the complex number proofs, what are skills we need to know? We need to know some of the basic, like, theorems on... You know, like for example, modulus of z squared is equal to a plus b. We can talk about that in this question, but we need to know some of the basic ideas. We can prove some of these. If we don't know, we can kind of always get to the right answer. But there's different ways to approach this. We can leave things in terms of my vectors z and w. But this question specifically actually says, hey, we want you to use that z equals a plus bi, and we want you to use W equals C plus DI. So it's kind of given us a little bit of a hint in terms of how it, I don't know why I said hint so hard then. I'm really passionate about the hint. It has given us a hint for how we can solve our question and what kind of steps we should be following. So we're going to do our substitution. When we're proving stuff, it's a left-hand side versus right-hand side battle. How do I know which side to pick? Normally, I pick the side that looks the hardest. It's kind of easier, normally. These are general trends. There's definitely exceptions. Everything in maths, there's like 65 exceptions. Normally, it is easier to simplify something than to expand things out and try to make it match normally. Like I said, 1,000 exceptions, but like typically that kind of works. So if I have that idea in mind, if I go this way, am I more in the center of the camera? There we go, just halfway through the video. If I keep that idea in mind, I'm gonna start with the right-hand side. Why? The right-hand side looks more complex. I know teachers that have the exact opposite philosophy. This is my philosophy, and it's my video, so it is what it is. So, when we have this situation, my right-hand side is equal to, I can sub in, I'm just going to write it out, so everyone that's watching is on the exact same page in terms of what I mean by the right-hand side. That is this side here. Okay, so I'm going to start by substituting in a plus bi. If I do that, I get a plus bi squared plus, well, w is c plus di. So that's going to be c plus di all squared minus 2 times the real parts of, we have some expansion here. I've got z, normal z, that is a plus bi, and I've got the conjugate of w, which is c minus di, and I'm going to put all that in one big bracket. Now, I said before about a complex number property, sorry, complex numbers and vectors are so similar sometimes. I might say the word vector like 7 times in this example. It is complex numbers, don't be confused. I just love vectors. I love complex numbers too. Anyway, so one of the properties I spoke about is this idea of, well, what happens when I have, the modulus of z squared, and I said it equals a plus b. The reason why it equals a plus b is because if I just consider what the modulus of z is, I'm just going to do this a quick little scratch at the top here. If I take the modulus of z, I get the square root of the real part, a, plus the imaginary part, b squared. I square each of those two bits, okay? Now, if I square the whole thing, my square root disappears. Sorry if I clipped the mic. My square root disappears. So that's going to mean I wind up with a squared plus b squared. If I have a squared plus b squared, well, that is why it's a squared plus b squared. So that explains that. And I can just do this straight away. I don't need to do any expansion and make it all look really messy. I can just take it out. This is going to give me a squared plus b squared. This part here is going to be c squared plus d squared for the exact same reason. The sort of more algebra challenging bit is this second part here, which is 2 lots of the real part of, I'm going to expand my brackets. I expand my brackets, I get AC minus ADI plus BCI, and I'm going to get minus, this part's important, minus BDI squared. Okay? Now, I can simplify this on the fly. Like, I wouldn't write I squared. Would you write I squared? It's a great question, right? You can. You're not going to lose marks. But I should know, especially at this point. I'm going to say I should know about a lot of things, right? They're things that I'd keep in mind if I was studying that I should know. But if you don't know at this point, it's also fine. But something to take notes of, I should recognize I equals the square root of negative 1. This is like at the beginning when we learn complex numbers. I equals square root negative 1. If I'm squaring the square root of negative 1, just like what we saw before, if I square a square root, the square root disappears, I'm left with negative 1. So I squared is negative 1. In other words, I'm just going to erase it to save myself a tiny bit of time. I don't need to write I squared. I can just times by negative 1. I've got negative BD times negative 1. That simply equals positive BD, because 2 negatives make a plus. So I just want to take the real parts. These parts in the middle with the i's attached, the i's do not have it. It's gone. Okay, apologies. Got another phone call. And I seem to be getting interrupted a little bit. So I'm back. Alright, so I kind of forget the last thing I said. I'm going to be honest. Kind of forget the last thing I said. I think I said something about the fact that the i's are now gone. I don't need to worry about those. So if I... What is that? Okay. I'm going to pause again. Gonna pause again. Give me 1 second. Let me fix the hurricane that has appeared in my room. It's like twice. Sorry. A lot of things happened. A hurricane appeared in the bedroom. A lot of things went wrong. So, I think the last thing I said was about I don't need to worry about the eyes. So if I come out here a little bit and I just kind of grab all my like terms, I'm going to wind up with a squared plus b squared plus c squared plus d squared minus 2 outside of just the real parts, that is ac plus bd. And I can leave it like that, or I can expand. I'll just expand. You can like leave a line and you can wait and see if the expansion is going to be helpful. That's also fine as well. So once I've done my right hand side, I've got to here, and there's nothing that I can really, there's no common factors, there's nothing I can collect, I can't factorize, there's nothing I can really do to try and fix any of these problems. At this step here, interesting. At this step here, I'm just going to see if I can do anything about the left-hand side. So I had like a little idea, but I'm just not going to go down that rabbit hole. We're going to look at the left-hand side. It's a simple, familiar question. Anything too crazy, I don't think is necessarily something we need to start to try yet. Okay. Yeah, okay. It's fine. It's fine. Sometimes when I get these ideas in maths, I just want to do it and see if it works. But we're making a video, so I'm not going to do that right now. I'm just going to keep with a more consistent method for you guys watching. So, again, I'm going to substitute a plus bi and c plus di in place of z and in place of w. If I do that, I get the modulus of a plus bi minus c plus di all squared, right? That is what the left-hand side is. Yes, that is what the left-hand side is. So I can now do my expansion. I'm going to wind up with a plus bi minus c minus di. Let me get rid of that little dot there. My bad. All squared. I can collect my real and my imaginary parts. I'm going to wind up with the modulus of a minus c. I don't need the brackets. I'm just putting the brackets in there so we can see clearly that that is the real part. And I'm going to have that plus my imaginary part, which is going to become b minus d, all outside of I. I'm going to square all of that. So, I don't know why I got a red dotted line. Leave me alone. I'm happy. I like it. Okay. My iPad doesn't like it, but I like it. I think it's great. So now, same rule as above. It's my real part squared plus my imaginary part squared, because I'm squaring a square root, so the square root part's going to disappear. I'm just left my real part squared plus my imaginary part squared. This time, my real part is a binomial, and my imaginary part is a binomial, but that is okay. That is going to equal a minus c squared plus b minus d squared, and this is where the idea I had before actually does work. Let's just do it. We don't need to do it. Okay. Some of you might have seen, and this is a little pause I had where I said, there's nothing, no common factors. I realized that I can actually factorize into perfect squares, okay? I can factorize this part here into a perfect square, and if you recognized that this here will make a perfect square, and this part here will make a perfect square, then we're actually done. We can match them. A minus c squared plus, I forgot a bracket, sorry, plus b minus d squared. That's fine. If you did not see there's perfect squares there, if you're confused what I even mean by perfect squares, just expand your brackets. You can match them that way as well. So if I expand my brackets, I can still match them. I get a squared minus 2ac plus c squared, and I get plus b squared minus 2bd plus d squared, which is the same thing I have above. The order's different, but it's the same expression. So therefore my left-hand side equals, I don't know why I'm writing so messy, equals my right-hand side, and we're done. Had a lot of room to that one question. Many ways to, get there to an answer. Okay, question 14. I'm going to pick up the pace a little bit because, well, I've had a lot of interruptions, so it's slowed down the process. Question 14. An object is projected. An object is projected vertically upwards from ground level after the object has been in motion for t seconds. Its position vector through the air is modeled by RT. So, I see a position vector. It's projectile motion. It's very likely I need to understand my relationship between position, velocity, acceleration via some kind of calculus, right? A lot of these questions require calculus, so I'm expecting that when I'm reading the question. Part D says determine the velocity, calculus, of the object through the air, VT. So I simply just want to differentiate. And I can just do that, actually. There's nothing stopping me. For a second there, I thought, is this going to be one of those? No, it's not. It's fine. I might need to consider the fact that things are in... Oh, no, things are in terms of time. Okay, so there's some rambling here. Apologies. This is the thought process when I'm solving exam papers is which bucket of question do I have? If we know with motion questions in general, we can have things in terms of position, or we can have things in terms of time. Time's the easy one. It's in time. No need to overcomplicate it. I was kind of looking for traps that just didn't exist in this question. There's no traps present. So it's simply just differentiate. To differentiate, I could product rule. Product rule. I don't want to do that. I'm just going to expand, right? That's pretty easy. For this particular example, you can product rule. Go for your life. 5 times 8 is 40. I get 40t minus 5t squared. I differentiate. I get velocity in terms of time. I should put all this as, brackets. All a j coefficient. If I differentiate, I get 40 minus 10tj, and I can put all of that in brackets as well. So, 2 marks. 2 marks? I guess, yeah, 2 marks done. Well, I mean, there's not more I can show. So, happy with that. I guess maybe expand is one, or I guess if you use product rule, you get 2. I guess there's some different ideas there. Part B, determine the number of seconds until the object reaches its maximum height. Well, we should know the object reaches its maximum height when the velocity equals 0. And if your teacher hasn't thrown things in the air for you to see that, I'm going to throw this paintbrush. No, it's a bit thin. I'm going to throw this marker. That's a bit better. If I throw stuff, okay, I don't have a lot of space to throw, but we should be able to see that whenever anything changes direction, like up, we change direction and we come down, we have to temporarily hit 0, like an instantaneous 0. Essentially, we go up, stop, come down. That's the idea. So the velocity is going to be 0 at the peak of the flight of the pen. Oops, the peak of my pen flight. I did catch that, and I just caught it down there. I swear. Yeah. So velocity with respect to time is equal to 0. Vt is equal to 0, and I'm simply just going to solve for the equation I found above, just the j component, right? That's the vertical component. That's the bit that I'm talking about here. I'm solving for that equal to 0, so I'm going to wind up with 40 minus 10t all equal to 0. I subtract 40 off each side, divide both sides by -10. I get t equals 4 seconds. Or I guess I can write 4s, right? 4 seconds, 2 marks. Let it equal 0, get the time. There are your 2 marks. Determine the maximum height that the object reaches in meters. So I now know the time, it's at its maximum. I don't even need to find acceleration. This question is pretty chill. So I'm simply just going to look at my position equation again. That is RT is equal to 5t outside of 8 minus t. J. And I'm going to put 4 in. Because that is the time when I reach my maximum height. I put 4 in. I get 5 times 4. I get 20. Outside of 8 minus 4. J. And I'm simply going to wind up with 20 times 4. 20 times 4 is going to give me 80j, which means I have 80 meters, because my units before... Wait, unless I got my units wrong. Well, yeah, in meters. There it is. In meters. I thought I read that. Okay, yeah, so it's in meters. So, look, honestly, question 14, easiest question so far, if we know what we're doing, right? So, basic theory testing, differentiate, solve for 0, and then just find the maximum height. Just note, it could very easily, in my opinion, just say part A, determine the velocity equation, done. Part B, determine the maximum height of the object. You would have to know to find time first, right? So you could actually really just ask you part C, could be the whole question, and you'd have to know how to do parts A and parts B without being prompted. Obviously, you're prompted in this case, but just be aware, to find the maximum height, that is step 1, that is step 2, that is step 3. So you could get just one question. We have to do all of that. Partial fractions? Oh, I haven't done partial fractions in ages. This is so exciting. Okay. So, I'm a maths teacher, to clarify. Why have you not done it in ages? I've been teaching in New South Wales recently, but I have also been a Queensland maths teacher as well, and it's just the way things shake out sometimes with what stuff you have to teach in a year. So it's been about... It's been less than 12 months, to be fair. It's been maybe 9 months since I've done a partial fractions question. So this is kind of exciting. I don't know how this doesn't come up in one of the other papers I've solved, but it's exciting nonetheless. So I want to start by doing my partial fractions, right? I've got my original fraction here. I should look at my denominator, and I should recognize that this part here can factorize, and they pretty much need to do this properly. So Two numbers that multiply to give -6, add to give -1 are going to be x plus 2 and x minus 3. So I factorize my denominator, that is step 1. Partial fractions is a over my first denominator, that is going to be x plus 2, plus b over my second denominator, that is x minus 3. I simply just want to figure out what my value of a and b is. To do that, I multiply everything by my denominator here. That is x plus 2, and that is x minus 3. I multiply by that factorized quadratic. I multiply everything through by that. Well, when I multiply this part here, I notice that the x plus 2 times x minus 3, well, the x plus 2 bits are going to cancel out, and I'm simply left with my numerator, 4x minus 17, equal to a outside of x minus 3, and the same idea is going to happen with part b, but in reverse, the x minus 3 is going to cancel out. I'm just left with x plus 2. That is kind of how our partial fractions work, okay? I know there's like tricks and shortcuts and all that stuff, but this is how we do it properly, okay? We get to here. I simply just want to make each part disappear. So I'm going to let x equal 3 for the first one to make a disappear. Then I'm going to let x equal -2 to make my b disappear. The reasons why it disappears is if you have a look, if x equals 3, I get a times 0. A times 0 gives 0. So I'm going to substitute x equals 3m to everything. And I'm going to wind up with 4 times 3 gives 12. 12 minus 17 gives -5. I know I did that part in my head. Apologies. You can pause the video, do it slower if that part didn't make sense on the left-hand side. 4x minus 17. 1x equals 3 equals -5. I'm now going to put that into my right-hand side, and I did the number 3 intentionally because I know that I'm going to get a multiplied by 0 plus b multiplied by 3 plus 2 is going to give 5, and I'm writing out this with all the steps. We don't necessarily need to for some of these. You can go straight to your answer. Okay, you can see what I'm left with is -5 equals 5b. Divide both sides by 5. I get b equals -1. I now do the exact same process, but I'm going to let x equal -2 now. If x equals -2, then I'm going to wind up with, again, I'm putting -2 into the left-hand side. Well, I'm going to wind up with 4 times -2. That's going to give -8 minus 17. That is going to give -25 is equal to a outside of -5. And my b part is going to, again, equal 0. I'm just not going to bother about writing it. It's going to be b times 0. It's going to disappear. So, if I do that, I get -25 divided by 5. I get a value for a equal to simply just the answer of 5. Okay, so I got an answer for b is -1. My answer for a is 5. I can now put everything back into my integral. If I put everything back into my integral, I get the integral of 4x minus 17 over x plus 2 x minus 3 is equal to, remember it was a over x plus 2, a is now 5, so I get 5 over x plus 2 plus, oh, I guess I put a plus there, right, but it's -1, so this is actually going to become minus, it's going to become minus 1 over x minus 3, and all of this, of course, with respect to dx, and I need my integral sign there as well, and I need a dx there, so we failed a little bit on the formalities, we fixed it, it's okay, we made it look pretty in the end. I now integrate each part separately. We should be aware this is going to give a logarithm of sorts. It's going to give a logarithm of sorts. I can bring my 5 out the front. I'm going to wind up with 5 multiplied by the natural log of x plus 2. And of course, yes, you divide by the derivative, but in this case, the derivative of my inside function, or my denominator, I guess, is going to be 1. So no stress about that. And I'm going to minus that by the natural log of x minus 3. Sorry, I had a little thought about the negatives there. Does that affect anything? No, I think I'm fine. And I have a plus c on the end here as well. So, I guess I should actually fix these. I should make these absolute value signs, right? This can't be negative. So, until I know what my values for x are, oops, fix that. I should put these in my absolute value bars to show that, there has to be a positive answer. So now I use my log laws. If I subtract, then that simply means I can divide, but I need to bring my 5 up as a power because I can't have coefficients in front of my natural logs. And I'm going to wind up with the natural log of x plus 2 to the power of 5 divided by x minus 3. Another phone call. We're popular today. Okay, so apologies. Pardon the interruption. because there were interruptions. I don't know why this got so messy. Let me just fix it. It's giving me the time to realize that I made a small mistake with how I wrote this number. This should be the number 5, right? Because it's the power of 5 that comes up. Other than that, that should be fine. That should be the right answer. And we're cooking. Happy days. Okay? So, that's my solution, right? Express my answer as the natural log, absolute value bars of a function plus c, and I've got the natural log, absolute value bars of a function plus c, so we're happy. It's a bit of a weird way to word it. I feel like this could confuse people. Do we need to do more? Do we need to show what function it is? But there's no indication about what the function's meant to look like. This is a form of function, so we are happy days. No expansion or anything like that required. We can simply just go to the next question. The next question is a proof by mathematical induction. Now we're cooking. A proof by mathematical induction. We should have practiced a lot of induction proofs by the time we get to the external. It's been in every external. In different forms, right? There's been CUs, there's been SFs, there's been CFs, but there's been multi-choice. But we're just, hey, what's this one little bit of the induction proof look like? But it's in every single paper. Sometimes it's in a multiple choice and it's also in the short response. Sometimes it's in tech free, sometimes it's in tech active. So no matter, or paper 1, paper 2, no matter how we cut the cake, we should have practiced a bunch of induction. We should be expecting to get an induction question. And can you believe it? I've got another phone call. Let's quickly jump into this proof of mathematical induction. There's an acronym that I like to use called TAPE for people that are just maybe aren't as practiced when we're learning. This could be an acronym we've seen. Again, we're in the studying part if we're watching this video, right? So TAPE's an acronym you can use: test, assume, prove, explain. That sort of helps you remember what the required steps are. Induction's a very formal proof, so you need to include every step to get all the marks. It's 6 marks as well, so it's pretty significant, right? So I want to start by testing, and I have a look at, is there any place in particular I should start? Normally, if we can, we like to start at 1, but sometimes 0 is the logical place. It's like a few different options that can happen there. It says Z's a positive natural number, so 0 is out the question anyway. 1 is a perfect place to start. So I just want to prove it's divisible by 3. I'm just testing basically that the premise of this is going to work. I'm going to start with the first number in my list, which is going to be n equals 1. So I'm going to test that n equals 1. And if I test n equals 1, I'm going to start with my left-hand side, right? Really, that's all I can work with. My left-hand side, I'm just going to show it's divisible by 3. So that's going to become 2 to the power of 2 plus 3 minus 1. That gives me 4 plus 3 minus 1. That equals 6, okay? I could write 6. One way to prove divisibility is basically to prove that 3 is a factor of something. So I'm going to write that as 6 is 3 times 2. So therefore, 3 times 2 gives 6, so therefore 6 is divisible by 2. So we can say therefore true for the first part. Therefore 6 is divisible. We'll go full explanation is divisible by 3. So my test step works. Now I'm into my assume and my prove step. This is kind of the bulk of where my induction work is. So I'm gonna assume that n equals k. If I assume that n equals k, then I simply just put k in place of n at every single step. Okay, and I get 2 to the power of 2k plus 3k minus 1. So we get 2 to the power of 2k plus 3k minus 1. And because I'm proving some kind of divisibility, right, we don't really have a right-hand side to work with. I've seen different ways people have done this. The way that I was taught originally, and the way that I still teach to this day, is I basically say, okay, that's equal to 3 multiplied by some number. Very similar to how I established 6 is divisible by 3 because it's 3 times 2. So I'm going to say, okay, it's going to be 3 times a number. I'm just going to pick the number p, or the letter p, I guess I should say, where p, for all values of p, that is an integer. Okay, so I'm just kind of establishing where p is a whole number, like 1, 2, 3, 4, etc. Okay, so that's part of what I'm establishing here as part of my proof. Now I'm going to do my required to prove step. So my required to prove, my RTP is n equals k plus 1. How induction works is I set up a back-to-back 2 terms in a row. I've got up to k. K could be the 4th or it could be the 10th term. Then I've got k plus 1. So if k is the 4th term, then k plus 1 is the 5th term. If k is the 100th term, then k plus 1 is the 101st term. No matter which pair I pick, I always get basically one number and the number directly after, right? It's kind of setting up the dominoes. There's a lot of examples and textbook pictures and videos about inductions, just dominoes. That's the dominoes idea. 2 dominoes to smack together to unravel the whole proof. So I wrote the letters RTP pretty messy. Apologies about that. I'll fix that right now, just in case people are looking at that and think, what the heck? I don't know why my R's... Okay, it didn't get better. Maybe I can't write the letter R. Sucks to suck. Alright, so I let n equal k plus 1. I'm going to wind up with 2 to the power of 2 outside of k plus 1 plus 3 outside of k plus 1 minus 1 equal to 3 times... Wait, I guess I use Q. P and Q. A classic, right? And again, I'm going to say for all values of Q that are an integer, I'm basically setting up that if n equals k, then k plus 1 should technically give a different answer. So I'm using a different letter to show to me 3 times a different number, right? Maybe p is 3 times 2, or maybe p is 2, so it's 3 times 2. Q could be 5, so it's 3 times 5. Or maybe q is 3, so it's 3 times 3, or something like that. I'm just kind of establishing that q is going to be an integer. And it's going to be a different answer than when I did n equals k. That's essentially what I'm trying to formally explain. Just pick 2 different letters. Happy days. That's the long and the short of it. If it doesn't make sense, it doesn't really need to. So now I'm going to do my left-hand side. So my left-hand side is going to be equal to just everything, and I'm going to ignore my 3q basically. So my left-hand side is equal to 2 outside of 2k plus 2. It may as well expand. Plus 3k plus 3 minus 1, which is just going to give 2. I'm just going to expand everything out because, again, may as well, right? May as well. I have to do it at some point. May as well do it when I'm establishing my left-hand side. To knock my dominoes together, for every induction proof, I need to combine my assume step and my RTP step. How I do that can change depending on a little bit, like, on your level of algebra skills. For me, I think a very safe flaw for these type of problems, especially if you struggle with divisibility, is I'm going to rearrange my assume step to make 2k, or 2 to the power of 2k, in this case, the subject, okay? I normally pick the term that looks, if it's got a power, I pick that term. A lot of these proof by divisibility have powers in them. So I'm going to pick this term here. That means I have 2, I'll write it in orange actually, we can see I've rearranged, okay? I got 2 to the 2k is equal to 3p minus 3k plus 1. Once I've done that, I'm now going to manipulate my left-hand side to get 2k as an expression. Okay, like I said, I think this is the highest floor way of going about solving proof by induction using divisibility. So if I look at my left-hand side now, I can see that this 2 to the power of 2k plus 2, I could rewrite that as 2 to the power of 2k multiplied by 2 squared. If we know our index laws, 2 numbers of the same base, add the powers. I can reverse my index laws if I have 2 powers being added together, like 2k plus 2, to split my terms back out again. 2 to the 2k times 2 squared is the exact same thing as 2 to the 2k plus 2, because if you think I add the powers, I get 2 to the 2k plus 2. So that's my first term. I'm going to split that, very common skill for divisibility by mathematical induction, and I get my plus 3k plus 2. I can now make my substitution. I can see, hopefully somewhat clearly, that hey, I got 2k in both spots. I can now put all of this here in place of my 2k in my proof by mathematical induction divisibility part. That is simply going to equal 2 to, that's not true, that's the part I'm substituting out. So that's going to simply equal, I might put my common factor here. I might bring that out the front, right? So I'm going to write this sort of backwards. I'm going to do 2 squared at the beginning. I could have just wrote that as 4, but whatever. 2 squared at the beginning, and then my 2k I'm going to put here just to make the expansion part a little bit easier. That is 3p minus 3k plus 1. Don't know why that took me so long to just remember what number to write down. Plus 3k plus 2. So I made my substitution. I can now go about and expand everything, right? If I expand everything, I should find I wind up with essentially 3 times q. Like, that's kind of where this is hopefully going to go, or something I can kind of create into a 3 times q. Actually, I guess the easy way to think of this is I should be able to expand, collect like terms, and take out a common factor of 3 out of my expression. If I do that, I've proven it's divisible by 3. So, if I expand, I get 4 times 3p, that gives 12p. I get, which is also, you can see, has a common factor of 3. 3 times 4 gives 12, so it's going well. I guess it should, right? It's got 3 in the number, so it kind of makes sense. I'm now going to do 4 times minus 3k, that gives me minus 12k. I'm going to do 4 times 1, that is going to give plus 4. And I've got another phone call. I'm back. So, expand the first bracket. I can now do my plus 3k plus 2. And if I collect all of my like terms, I wind up with this equals to 12p I have minus 12k plus 3k, that's going to give me minus 9k. And I got 4 plus 2, that's going to give plus 6. So you can see here, I have a common factor of 3. I have 3 outside of 4p, minus 3k, plus 2. So I've got my common factor of 3, basically. I can simply now say, okay, well, that means 4p minus 3k plus 2. I'm going to say all of that is equal to q. Again, q was just a number. This is going to give me a number. So I can say, whew, almost at the end here, I might need to grab this all a little bit and just make this a tiny bit smaller. Hey, I said rearrange, tiny bit smaller. There we go. Thank you. And I can get my final answer of equal to 3q, which equals, I'm going to put a comma and just write this, equals my right-hand side QED. Whew, okay, we did it. Now I do need to write my explain step. Oh, I have a page here. I'm going to write my explain step here. If I knew that, I didn't have to lasso everything. But I'm going to write, therefore, there's many ways to do this. I keep it pretty simple. Tested for n equals 1. True. We did test for n equals 1. Awesome. Assumed true. Assumed true. You can actually basically write the same thing on all of these induction proofs, more or less. Sometimes there's an exception, but for the most part, something like this is a good basis to have. And we proven true for n equals k plus 1, assume true for n equals k, and proven true for n equals k plus 1 by mathematical induction. Mathematical, really good handwriting, induction, and that would be enough to get the 1 mark, I think, is actually assigned for the therefore statement. Okay, I'm back. I took a little break. I'm back. And we're going to finish off this paper full steam ahead. Let's get into the last complex familiar, and then we'll tackle the complex unfamiliars. We have question 17, looks like a volumes of solids of revolution type-based question where we're finding a boundary between 2 curves. The 2 curves themselves is a straight line and a quadratic, so they're very familiar graphs. When we have situations like this, we should consider what axis am I revolving my object around. Okay, it's around the y-axis, so that does change things a little bit, right? It makes us have to consider things slightly differently than maybe we'd prefer to, or the way we normally do it, where we mainly consider our x-axis, where we rotate kind of, I'm gonna say like the normal way, like the more common way of going around this way, as opposed to going around sort of the vertical axis. So I think it's worth drawing little mini pictures. It does not need to be a detailed sketch. Okay, this needs to be like a rough sketch, so you get a bit of an idea of what's going on. There's my straight line. It's not perfectly 4x, right? Like, it's about 45 degrees, but it's fine. Again, the idea here, nothing's going to be perfect. We can see my y-intercept for my straight line is 0, so it's going to pass through the origin. And we can also see the same thing is true about my quadratic. So I'm going to want it with 2 graphs that look like this. And if I know anything about how these shapes work, I'm going to make it a bit exaggerated so we can see that we clearly get this little gap here, and they're going to intersect at some point. What's a good color to pick? I think pink is always the best color choice. We got a little point here, although it does look a bit like orange. We got a little point there. Okay, so we need to find 2 points. It's going to intersect there. It's also going to intersect here. So we want to figure out what I normally refer to as the boundary. What is the boundary I'm going to be rotating my object around? So, in order to do that, I'm going to get my blue pen back. And we are going to find... Have I been doing this color the whole time? No, I have not been doing this color the whole time. Let's keep it consistent. Let's use the darker blue. Sometimes I don't know which one I prefer more. We're going to find the boundaries. Okay, I'm just writing this down really for people that are watching. That way they understand, okay, what's step 1? Oh, I don't think I spelled that correct. This is where I like to point out that I'm a maths teacher. I'm going to write it. Boundaries? yes. Someone in the comments, please correct me. And you can be really mean about it too. It's fine. I should know this. I'm an adult. But I don't. We all have our flaws. We all have our flaws, okay? You know, I can admit mine is spelling like plurals, I guess. Alright, so this little bit here in the middle, that is the part I'm going to be rotating. This bit between my 2 curves. I'll zoom in so we can see that nice and clear. Okay, so that's the bit that we're going to be rotating around. And we are rotating specifically around the y-axis. So what this changes is, when I'm revolving around the y-axis, actually the curve closer to the y-axis is going to be my green curve here. Okay, that's the closest one to the y-axis. I don't know why I chose green for the color as well. But that basically means we get down to the function bit. I'm kind of explaining this in advance. We get down to the function bit. I'm going to be using my orange curve, the quadratic, minus the straight line. If it was the x-axis, it would be the opposite way around. But because it's the y-axis, I do the thing furthest away from the y-axis minus the thing closest to the y-axis. So it does change the perspective a little bit. But we want to figure out what these two pink dots are in terms of coordinate points. We can find one of them straight away, right? Like, we know one of them is going to be 0. But let's find the boundaries the proper way. I said the proper way. Let's just do the whole thing, right? Assuming it was harder, we'd have the same steps. A robust method. No matter how it changes, we do the same steps every single time. I notice both of my equations are equal to y. I'm going to equate my equations, okay? I'm going to use simultaneous equations to find points of intersection. This, hopefully, is something we've seen before. So if I equate my equations, then I'm basically saying, okay, well, that means that 2x squared is equal to 4x. I'm just putting my power 2 on the left-hand side. But you can swap the sides, you get the same answer. So I'm going to get that. I'm now going to subtract 4x off each side. I get 2x squared minus 4x, all equal to 0. I can take out common factors. I got a common factor of 2x. So I get 2x outside of x minus 2. And I'm going to get two solutions when it equals 0. I'm going to get x equals 0, which we expected because you know it passes through the origin. And I'm also going to get x equals positive 2. So I found the two x coordinates where I have a point of intersection where those two pink dots are. I just need to find my y coordinates to have complete sets. Now, I can pick either equation I want to substitute these values into. I'm just going to choose y equals 4x because it's the easiest. If x equals 0, I'm going to write it out just because I can, right? When x equals 0, y is going to equal 0. So one of my coordinate points, I'll put it in green. That is going to be 0, 0. And my second coordinate point, I'll also just keep the colors kind of consistent. We can set this out. There's like ways to communicate. We're never going to be too picky on things like this. We just want you to actually clearly demonstrate that you know what you're doing and explain where those coordinate points come from. Don't pull them out of thin air, but it's something really basic like what I've written in orange is fine. There's better ways, there's longer ways, there's probably shorter ways too, but that's just what's come off the top of my head in the exam. Don't overthink it, you'll be fine, right? Just try to make sure you're practicing the same way in your practice papers as you're going to do on exam day. So when x equals 2, again, I'm substituting into the equation y equals 4x. So when x equals 2, y equals 4 times 2, so y is going to equal 8, and I get the coordinate point 2, 8. Nothing too complex here, just a basic substitution, get two coordinate points. So I found specifically the x coordinates maybe not the biggest deal, right? But these y coordinates matter because we are doing our revolution with respect to the y-axis. So I know my boundary when it comes to integration time is going to be between 0 and 8. Okay, just kind of setting the scene for where these numbers are going to come from. But again, this is something that we should be aware of, hopefully. And if we're not, then hopefully this is making sense and we're following along. So once I establish my boundaries for the y-axis, I can now get into actually making my equations differentiable. So to make my equations differentiable, like I said, the language, we have flaws we can improve on. But to make my equations differentiable with respect to the y-axis, I need to make my equations in terms of y. I need to find f of y is kind of one way you might have seen this written before. In other words, my two equations, to make this make sense, my two equations of y equals 4x and y equals 2x squared, they are the right equations. Let me just, yep, that would be awkward if I started solving the wrong ones. I need to make each of these with, basically I need to make it x equals in both cases, right? I need to make x equals something. So I need to make x the subject. So I'm going to divide both sides by 4. I get x equals y over 4 or a quarter times y, both are fine. If I do the same thing with the other equation, I'm going to wind up with x squared equals y over 2. I square root both sides and I get x equals the square root of y over 2. I could write this a few different ways as well, but I think this is fine. Yeah, it's fine. So I get my two equations in terms of x. I remember from above that it was the quadratic that was the furthest one away. So I'm going to be starting with my quadratic, then I'm going to go to my straight line. So it's going to be this equation here, that's going to be equation 1. I'm going to minus that from this equation here when it comes to establishing my integrals. So if we can remember how to do volumes of solids of revolution, we square the function. Okay, we're doing it with respect to the y-axis. So we can kind of set this up a little bit. Do I have another page? I do, because this is taking up heaps of space. Maybe we'll go to the next page and I'll establish this. My volume for solids of revolution is equal to, we're going to use exact value bars because I have a subtraction. Maybe I'll talk about that a little bit. I'm just going to put it there for now. It's pi outside of the integral. My boundaries were 0 to 8 of my function with respect to y, dy. And I'm going to minus that with the same boundaries from 0 to 8 of my inside function, the one closest to the y-axis. I'm going to call that g of y, and we're doing that again with respect to y. And sorry, I missed my pi outside of that as well, okay? I could probably I could probably fix all this up a little bit now I think about it. Like, I don't really need these two parts. Everything's going to be integrated. Pi is out the front of all of it. So I've really kind of got, like, I can get rid of this to y here as well. I've really got a situation where, hang on. Yes. Oh, wait, I missed a step. I'm going to leave it like this. Let me just put this part here in to make the brackets a little bit neater. So I started writing it, and then I thought I can kind of simplify this to make it easier for people watching along. I don't know if I did a good job of that, so apologies. I'm going to see if that grabs everything. It actually did. That's kind of nice. So basically, I get this expression here, where I have pi outside of everything. I'm just integrating the whole thing between 0 to 8. I did it in two separate integrals before. You can do that as well, but let's just bring the whole thing out the front. It's just one big integral, right? I got one big integral, pi 0 to 8 of my function furthest away minus my function closer. I square each individual part of the function, and again, I should include these. That's not my pen. I should include these absolute value bars because volume can't be negative. It shouldn't be negative because I set it up the right way. I probably, the more I think about it, maybe I don't need to put the absolute value bars. I'm doing the furthest one away minus the inside one. It should give me a positive number, but like formalities, like this is normally how we set it up. I wonder if this covers you if you get it the wrong way around. Either way, this is like how you see it in most textbooks for these type of questions, where we get these absolute value bars. We can't get a negative volume, so it kind of makes sense. Once we do that, I just simply actually go about, well, f of y, I'm kind of saying that's my furthest one away. That's going to be my quadratic. So that's going to be, if I substitute everything into this formula here, I'm going to have the absolute value of pi outside of 0 to 8. F of y is my thing I've circled in yellow here. That is going to be the square root of y over 2, all squared, very convenient, minus, if I've got my g of y, that is simply just y on 4. That is y on 4. It is going to be y over 4, all squared to y. And again, absolute value bars. So I'm just substituting in my functions. I'm squaring each of them. I'm now going to actually just go about the calculus part. I'm going to get rid of the square root part here as well. I'm going to write one more line just because I want to do my integral without the square root. That's going to give me y over 2 minus y squared over 16 with respect to y. And I can put my little absolute value bar at the end there. Again, I don't know. Like, I'm kind of thinking, like, sometimes you know, there's these processes that we follow, and I don't know if it's going to make a difference in this case, but we're never going to be wrong for using the absolute value bars, I guess. So, like, let's just not overthink it. Let's just use our brain power on actually integrating our functions, which aren't too challenging. So if I integrate my functions, it's a definite integral. I'm going to put my pi symbol at the front here of everything. Put my absolute value bars in here again. I don't really need pi inside the absolute value bars. It's already a positive number. So I'm going to have the definite integral of, if I integrate y divided by 2, raise the power by 1, divide by the new power, I'm going to wind up with y squared over 4. If I do the same thing over here, I'm going to wind up with y cubed. Now I'm going to multiply 16 by 3. That's going to give 48. And that is all between 0 and 8. Again, I got some absolute value bars here as well. Okay? Which I think I'll be fine with. But it's fine. We're covering ourselves, right? We're just making sure that there's no possibility we can make an error. And we're demonstrating good understanding about how this works. So again, we're ticking our boxes. If they're redundant, it's fine, right? Like, again, we're not going to lose marks for putting it in, and we're saving some of our brain power. I'm going to have pi outside of, let's actually substitute in our values of 8. If I put 0 in, it's all going to become 0 anyway. So we're really just substituting 8 into the equation. That is going to simply give 8 squared, that is 64 over 4, minus 8 cubed. 8 times 8 is 64. 64 times 8. 64 times 8. I have to think about this a little bit. Hang on. We're going to trick it. True, right? True? It is true. 8 cubed. 8 times 8 times 8. 8's a factor of 48. 8's a factor of 48. So, if 8's a factor of 48, it is right. It is right. 8 is a factor of 48. Am I losing my mind here? It is. 8 times 7? Wait. 8 times 8 is 64. 8 times 7. 8 times 6. 8 times 6. Wow. The brain started to dissolve for a second there. Okay. So, to explain what's happening, to make this clear for everyone watching, it's tech-free. I don't have a calculator. So, God, 8 times 64 is kind of difficult, but I've got this 48 on the bottom, so I'm trying to simplify a little bit, right? I can split 8 cubed up into 8 times 8 times 8. 8 goes into 48 6 times. So what I actually wind up with here is 8 times 8 over 6, or 64 over 6. So I'm going to clean this up here a little bit. I can simplify it further for everything here, right? This is going to be pi outside of 64 divided by 4 is going to give 16, minus 8 times 8 gives me 64 over 6, which both even numbers, I can halve both, I get 32 over 3. So I'm going to fix this up and make this 32 over 3, so I don't have to write 1,000 lines. We're just trying to simplify down our fractions here a little bit. Again, it's a tech-free paper, and yeah, I'm not going to need my absolute value bars. I don't think I ever needed them. I don't think I ever needed them because I did it the right way around to begin with. And I started questioning myself for why I'm putting these on, but it's fine. Like, it's fine. It actually is fine. I'm going to get rid of them because I can see I don't need them. I'm just going to get rid of them. And maybe I could have got rid of them earlier on. And again, like, in exams, I would say there's a lot of little tricks. Some things don't take you any more time. Like, things like putting absolute value bars in don't take a bunch more time. It would be marginally more efficient to not do it. Like, I didn't need it because I was doing the bigger number minus the smaller number. It should have worked out fine anyway. However, let's say you messed it up. You have your absolute value bars in. That kind of does cover or protect you in case there's an error. If you get a negative volume, you can take the magnitude of that number, get the positive answer. So we're really just having ways to cover ourselves in case you make mistakes. Because, end of the day, about 5 to 10% of all marks lost in the external exam come from messing up positive or negative signs. So little things like putting absolute value bars in the right spot can help negate making any errors. Although in this case, I never really needed them, and I kind of, part of me realized it's fine. So if I finish all of this off, I've got pi outside of, I want to make everything over the same denominator of 3. So I want to times 16 by 3. 16 times 3 is going to give 48. So I'm going to get 48 over 3 minus 32 over 3, which is going to equal, that's 16 over 3. So it's going to be 16 over 3 pi units cubed. And I feel pretty good about that for the answer. Okay, nice. So we did look at some strategies here to help break up some bigger numbers to simplify our fractions a little bit easier. Which I actually do think, like, we need to know some of these facts, right? Or these little tactics we can employ. So, that's 7 marks in the bank. And actually not too bad. Like, a lot of steps. Like, it looks big when you zoom out and look at the whole question. But each individual part, not so crazy. We are now slamming headfirst into... Wait, do I have 1 question left or 2 questions left? Two questions left. So, they're both going to be complex, unfamiliar, most likely. I don't know if the QCAA ever releases the actual, like, question grades for is CU. I think some websites have some ability to claim or track, but it's 20% of the marks, right? So we've got, what, 6 marks here. We've got another 7 marks there. It's probably about 20% of the total marks of the paper. So it makes sense that this is your complex, unfamiliar questions. It's normally in order. Final 1 to 2 is normally CU. Normally it's final 2. Sometimes 2 to 3, I guess I should say. Final 2 to 3 is CU. You can have 2 3 markers and a 7 marker. You can have a 6 and a 7. Yeah, you just normally, 6, 7. All right, whatever. I did the thing. Okay, so this differential equation can be used to determine the current and time with voltage V in an electric current containing a resistance R and ohms. What is happening? Sorry, I just read that question and realized I'm not actively reading. I'm just saying things out loud. This differential equation can be used to determine the current at time with voltage in an electric circuit containing a resistance R ohms. Okay. I actually have done a lot of physics in my time, so the physics questions tend not to scare me. But when you are not expecting it, it's like, what is happening? K, R, and V are positive constants, feels important. Because this is a greater than 0. I guess T is greater than 0, that part doesn't matter. It feels important, right? Positive constants, and these are just going to be individual numbers. What am I trying to find? Assuming there is no current in the electric circuit initially, okay. Show that the size of the current... Initial conditions are always important. So I equals 0 when T equals 0. Show that the size of the current can never be greater than the volts divided by the resistance. So this is actually like a physics proof, but we can use it using differential equations. So, I need to have a little think here. Let me have a little think about how we want to approach this. I got K di dt plus Ri equals V. I want to get V over R. So I'm going to need to get rid of the differential equation part, the di dt. I'm going to have to integrate to do that. And then I'm going to try to get my V and R on the same side. How hard could it be? It's a complex unfamiliar in the specialist exam, so probably harder than I'm expecting, but it's fine. I'm up for the challenge. All right, so I have to lock in a little bit here. Let me write out the formula. If you're in doubt and you're in this stage where you're like, what is happening? I'd recommend some tips around using your reading time. Read the CU questions that don't surprise you, and your brain has a little bit more time, even if it's working in the background, a little bit more time to think a bit about what is coming up at the end of the paper. It can actually really help make a big difference, especially in a timed exam. So, I want to get my differential equation parts with the right parts. Nailed it. So, this implies a few things. I want to rearrange. Yeah, okay. I'm going to minus Ri off each side. Yeah, okay. I minus Ri. I minus Ri off each side. And I'm left with K di dt. Okay, so I'm trying to get my derivative part by itself. V minus Ri. Okay? So at this point here, I think I can just keep the K. I want my di's with my i's. So I really need to, like, multiply, divide. Yeah, I need to multiply, divide. It's probably the easiest way to get to my answer. So I want my di matched with my ri. And you might be thinking, well, you had it on the same side. But I want it like as like a, you know, a common thing out the back. So we're trying to find a way, really, to get my di with my I, my dt. There's no dt's, but so my dt can just disappear. So I can integrate both sides, right, the proper way. So if I do that, I'm going to multiply both sides by dt. It needs to be a common factor of everything. That's basically why I had to get rid of the ri to begin with. And I'm left with k di equals v minus ri, in brackets, multiplied by dt. I can now divide both sides by v minus ri. Gee, this is like a little... You have to see this, like, kind of... like, sorry, starting CUs can be a little bit rough, right? But, like, this is something, like... It's hard. We hopefully know, and if we don't know now, we do know, that when I get these differential equations, I want to pair my variables with my... If I have a di and I have an I want to get those together. If I had a t, I'd try to get my t's with my dt's. I don't have t's, so I can't do that, but I do have an I. So I can get my i's with my di part. So I'm going to divide both sides. I'm going to write it like this. I'm going to write this as k divided by v minus ri, just because this makes it easier for us to integrate, di, and that's simply just equal to dt. I can now integrate both sides. So if I integrate both sides, I wind up with, well, it's going to be a log, right? It's going to be k, that's my constant, k is a constant, outside of the natural log of, I'm going to use my absolute value bars because we don't, well, we don't know if they're negative, like, it can't be negative. V minus ri. Okay, let's just leave it like this for now. I'll think about this a little bit more as we're solving, but I should use absolute value bars, like, just generally, it's good habits. So that's my derivative of this part. Wait, hang on. I want to divide by the derivative, so I need to divide by negative r. There we go. We can pick a little bit where we put our plus c here. I'm going to put my plus c on the right-hand side. If I integrate, I can kind of think of this as being like there's a number 1 here. So I'm basically integrating 1 with respect to t, well, that's going to become 1t. So I'm going to be left with t, and my plus c I'm going to put on my right-hand side just because it seemed easy. I could put it on the left-hand side too. It just seemed like that made sense for where to put my... sorry, I'm putting my fingers in front of my mouth like a child. It just made sense where to put my c because I've got a natural log on the left-hand side. I'm going to make I equals 0, okay, because we read the question properly. We know that my initial conditions are the current equals 0 when t equals 0. So t is going to equal 0. I'm going to be left with c equals something, and that seems better. Basically, that just seems better. If I put my c on the other side, I can still get the same answer. So it doesn't really matter where you put the c, just pick one side. I know some people put it on both and combine them and all that, whatever. You can just put it on one side, you're fine. So now I can do my initial conditions to find c, and this is something that's practice. This is almost a simple familiar skill of, okay, I've got c, initial conditions, my initial conditions, I'm trying to zoom up here, scroll up, sorry, in the question is no current initially. So I know initial implies time equals 0, I equals 0, I'm going to write it here just so we can all see, t equals 0, I equals 0. So I'm going to be left with a pretty simple expression, that is c is equal to, because it's 0 plus c, I just get c, And I've kind of swapped the sides around. Sorry, I almost skipped a few steps. Hopefully we can follow right. If I put t equals 0 in, I just get c on the right-hand side. I'm just putting that bit first so we can save a little bit of space. That is going to be equal to, we'll put the negative here, k divided by r, natural log of, well, I guess it's the absolute, oh no, I don't need to put that in because absolute value, like voltage, we know V is a positive constant. So I don't need my absolute value bars around my V, and I get this value here for my C. Okay, so I get this value for my C. I can put that back into my question, and I'm going to wind up with negative k on r natural log of, I need my verticals, V minus Ri equal to, oh yeah, whatever, we'll just put it here, t minus k over r natural log of V. Okay, so do I want to get t by itself? Like, is that worth my time? Do I want to just add this and I should have left c on the other side all along? Sure, the size of the current can never be greater than V. Okay. I want to get rid of the coefficient at the front. Making it a power seems awkward. I want to get rid of the natural log part. So I want to raise everything to a base e. Okay, these are the steps that's going on in my brain right now. I want to raise everything to a base e. Okay, if everything is raised to a base e, then hopefully I can, this V minus Ri part, like it's not that difficult to squint and see I could rearrange that to I equals like V over R. If I just think about what's inside here, if that just equaled 0 right now, for whatever reason, I could subtract V off each side. I'd simply get I equals V over R, which is very similar to what we're trying to show here. That current, it's a greater than less than idea, but it's very similar to how I could get to this expression. So recognizing that like I'm here makes you think, okay, that there's sort of a right track idea, but I want to get rid of the absolute value bars. I want to get rid of the log part. So I need to raise both sides to a base E. I also got a natural log on the other side as well. To raise both sides to a base E though, I can't do that if I have a coefficient in front of my natural log. I need to get rid of this minus k over r. And you can see it's actually in two spots. It's the coefficient of both, and it's the same coefficient. Okay, so some ideas are forming. Sometimes it's good to just talk things out, actually. So both sides have negative k over r as the coefficient of the natural log. Okay, I'm going to multiply everything by this. There's a few tactics to get rid of this. The easiest one that I can see is I'm simply just going to multiply everything by negative r over k. I'm going to let that sit with you guys for a second. If I do that, my r's cancel, my k's cancel, and it's gone. I'm multiplying by the reciprocal of my coefficient of the natural log, which works for everything. This literally works for everything. But I have to multiply every single term. So multiplying that by this, I'm going to multiply this by negative r over k. I'm going to multiply this by negative r over k. If you multiply by anything, it needs to be consistent the whole way through, right? So, and again, r and k, they're constants. They're just numbers. We don't know the number, but they represent a number. So I'm not multiplying through by variables or anything like that. Well, I guess they're technically a variable, but they're a constant variable in the context of the question. So, multiplying through. Basically, I get everything I want. My coefficient's now gone, which is great. I'm going to put my answer on the next page. So I'm simply left with the natural log of V minus IR equal to negative, let me get this the right around, it's R over K now. We've kind of flipped everything. Negative, whoa, R over KT, because I have to multiply that by the T. And in the case of the T, it doesn't cancel out. I just have this new, very awkward-ish looking coefficient, but we're going to see if we can work with that later. Hopefully we can work with that later. And that is going to be plus now, because I multiplied by a negative. It's going to become plus the natural log of, I don't need my square brackets, I just need my little brackets V. Okay? I now raise everything to a base E. If I raise everything to a base E, I get V minus RI. I no longer need the absolute value bars because it's no longer in a log. It can be negative. It's fine. We don't mind. That's going to be equal to E, so the negative R over KT plus V. Hang on. I almost made a big error. And sometimes I have to pause after each step and just make sure we're on the right track, okay? Even me. So, I can't raise each term to a base E, like I was doing there. I can't raise the first term to a base E and the second term to a base E. If I raise something to a base E, the whole thing raises to a base E. The whole thing. that means I actually get, I know my R's are just terribly messy today, so apologies about that. I actually get this plus the natural log of V. It's all up here in the power. This whole line here has to raise up to there. I nearly made like a really basic math mistake there, almost. So that's what it should look like, okay? I have to raise everything up. But the reason why I was like, oh, but the natural log and all, it's going to cancel. It is going to cancel. It just cancels a little bit differently. We spoke about this before with proof by mathematical induction, that a skill we need to know is how to split an exponent, okay? What I mean by that is when we're adding exponents like we are here, I need to be able to break it up into two terms using my base, kind of reversing my index laws. So I essentially get e to the negative rkt multiplied by e to the natural log of v. What this means is that now my natural log of my e cancel. I'm just left with v, but instead of it being plus v, it is actually being multiplied by v, which is going to make a very big difference to our final solution. So what I wind up with is v minus ir equal to v outside of e to the minus r. That is the letter r, believe it or not. R over kt. So I'm here. God, I've done a lot of steps. It looks good, right? This question, you know, sometimes with the CUs you start them and it unravels really nicely. It starts to kind of get more and more obvious. This one, each step is actually like a lot of brain power. Okay, so I'm here. I'm trying to prove that I is greater than... Okay, I'm having a long pause here. Having a long pause while I consider what's going on. The idea here is pretty abstract. It's pretty abstract. Okay, so basically, the question has this idea of... Let me go back and show the question and where my brain has gone with my thinking time and why this question is legitimately pretty challenging. I'm going to be honest, most of the paper I feel like you'll find, it's not bad. This question has like a lot of thinking. Okay, K, R, V, all positive constants. T has to be greater than 0. Okay, that's something that's important to note. We are assuming the size of the current can never be greater than V over R. So greater than, we don't really need an equal sign. We need a greater than sign, right? Equals isn't going to help us in this case. So I need a greater than sign. Well, how can I get greater than sign? And what about this positive constant stuff can help me get there? If I know V is always positive, essentially what I have here, this is like pure math theory, but I think it works, and well, I think it works well in this case, is I have a positive number, V, multiplied by e to the minus r over kt. Well, I know my base e is positive. I have a negative indice. But does that change the sign? And the answer is no. There's no power I can possibly put. There's no number combination I can get that exists in the universe that I can put on my base of e that would make it negative. I can make it very small. Like if I consider, you know, e to the, I'll use this as an example, e to the minus, 100, that equals 1 over e to the, I did 1000 over 1000. That's a very small number. But it's not negative. It's still a positive number. In other words, no matter what happens here, no matter what my value of r, k, or t is, I have a positive number multiplied by a positive number. Well, two positives. And by the way, e can't be 0. And v can't be 0 either. We kind of learned the question, so it can't be 0. I'm going to have two positive numbers. If I multiply two positive numbers, I'm guaranteed to get a positive number. And I feel like I've said the word positive like 65 times. But all this is to say is that v, e to the minus r over kt, is greater than 0. Like, it is a positive value. It has to be a positive value, which means if v minus ri equals v e to the negative r over kt, it is also greater than 0. Ding! So we get our greater than sign. We wind up with v minus greater than 0. I can now rearrange. And the thing we saw all the way back here. Okay, wait, did I erase it? Did I erase it? Wow. Remember here I mentioned, hey, if it equals 0, I can rearrange it. It looks good. That's basically where I thought I could go. It's where I've wound up. I want to make I the subject. I'm going to minus v off each side. Remember, if I'm minusing, the sign stays the same. It's only if I multiply or divide by a negative that I get a switch around, okay? So when I minus the v, the sign's going to stay the same. I'm going to wind up with negative IR is greater than negative v. Now, when I flip it around, okay, when I do it the other way around, I'm going to divide by or multiply by 1 over negative r, however you want to think about it. I'm going to wind up with my current is less than v over r. They're both going to become positive. So therefore, if my current is less than v over r, wait, less than, show the size of the current can never be greater than, okay, yeah, that shows it, right? I guess I could flip it. I could say this, v over r is greater than I. In other words, my current is always going to be less than v over r, or v over r is always going to be greater than my current. I can word it a few different ways, and I've solved this question legitimately so far easily. It kind of went, these are all kind of fine. Boom, and the difficulty ramped up quite a lot for this CU. I imagine this made people very sad on the exam day. So therefore, the current can never be greater than v of r. I'm really just rewording the question there. And I'm very happy with that work. Like, I'm really happy with that. Okay, so final question. I really needed to bring my water for this. Final question. Oh, it's vectors. Okay, this is probably going to be nicer. The velocity of two objects, I say that. The velocity of two objects, differential equations just has a bit more of like how long is a piece of string. Like they can just kind of go off in all kinds of directions. The velocity of two objects, A and B, in meters per second, in time t are given respectively by my velocity of object A is 6 sine 3t. Okay, yeah, velocity of object B. Objects A and B are initially at initial conditions. Very good. Maybe I should get my highlighter out. Okay, determine the position of object A when it's 4 meters away from object B for the first time. Okay. So, I've got a bunch of velocities, and it's everything in this question is about position. And I know if I integrate my velocity at position, and I'm given initial conditions to find C. So, like, honestly, question 19 looks okay. I'm gonna call it early on. It looks okay. So, I've got velocity of particle A, object A, whatever, is equal to 6 sine 3ti plus 6 cosine 3tj. Okay, I now want to integrate to get my position. If I integrate, I get my position of particle A with respect to time. I'm just going to use that so I have some function notation to use later on just to make my life a little bit easier. If I integrate everything, maybe I should have written integration signs or whatever, but I think it's okay. I think we get where we're going with this, and I think you'd probably find it exam marks wise. If I integrate sine. Well, if I differentiate, sine goes to positive cos. If I integrate, it goes to negative cos. And of course, I divide by what's inside my derivative. So I'm going to wind up with negative 2 cosine 3ti plus, yes, plus, sorry, I had a little pause there, plus cosine goes to positive sine when I integrate, plus I'm going to get 2 sine 3tj. So that is my position vector for RA. And I should put in, I've also got a plus C because, of course, I integrated. I may as well find my C now. I know my initial position for A is... Oh, okay, yep, okay, that's interesting. So I actually got... Talking too quick, let me take a second, sorry. Why it's interesting is both of my velocity vectors are given in terms of I and J. There is no K component. However, in both of my coordinates, this is saying it is 3D. We have a K. There's just no K in the velocity. It doesn't mean there's no K in the position. My K is going to appear in my C value, most likely. I mean, yeah, it is, because that's just how these questions normally work. So initial implies T equals 0. And I'm going to actually write, because I've put everything in terms of I and J, I'm going to write my minus 2, 0, 2, if we're not sure where those numbers come from, this part here, okay, this bit here. I'm going to write that out in terms of I, J, and K. I'm going to write it almost as like a column vector, but I'm going to put I, J's, and K's because I've got my other vectors in terms of I, J, and K. So, that is, when T equals 0, I'm going to have minus 2I plus 2K is equal to minus 2 cosine of 3 times 0. I don't really need to put that in. It's not a 10, it's a 0. Let me just try to fix it so it looks proper. I'm just going to write it of 0. We don't need to write 3 times 0. I'm going to leave it like that. Plus 2 times sine of 0, J, plus C. So if I consider that, well, cosine 0 is 1. Sine 0 is 0. So what I wind up with here is minus 2i plus 2k is equal to, well, minus 2i plus c. Okay, my sine part's going to disappear. We're just equating, right? We're equating to find our initial conditions. I'm going to add 2i to both sides. Well, minus 2i plus 2i is going to give 0. So if I add 2i to both sides, then both of my i's are going to disappear, and I'm left with c is equal to 2k. I can now put that into my position, and I get a final position vector. Therefore, my final position vector with respect to time is minus 2 cosine of 3ti plus 2 sine of 3tj plus 2k. Got it. Okay. Basically, we now rinse and repeat for vector b. We do the exact same thing for vector b, so we're going to integrate again. I'm going to write out vector b. Vector b, I'm going to put it just in terms of t immediately. I didn't do it here. It's little things. I don't think anyone's losing marks because of things like this. If I do vector b, let me scroll up. That's cosine ti minus sine t. So a few less numbers to worry about. That's kind of nice. If you have to do the whole thing again, it is minus sine t, right? Yep. Minus sine tj. So they made it nice the second time around. It's going to be less things to worry about. Therefore, I have a position of vector b with respect to t of cosine goes to positive sine. I simply just get sine ti plus cosine tj plus c. Okay? So, pretty basic integration. Again, my initial conditions, I'm going to equate just like I did before. I have 0, 1, and minus 1. That is going to become j minus k is equal to sine 0, which we know is 0, I plus cosine 0, j plus c. And I basically get a very similar situation happening. I have j minus k equal to j plus c. And again, the j's are going to disappear. Subtract j of each side. J's are now gone. My c value is simply just going to be negative k. So c equals negative k. And I'm going to put that back in. And I get my position vector for b is equal to sine t I plus cosine t j minus k. So I'm going to zoom out. I'm going to highlight. I didn't put therefore dots. I put therefore dots to make it also obvious. These here are my two position vectors that I need. I want to figure out the position. I want to figure out the position of object A when it is 4 meters away from object B for the first time. When it's 4 meters. Position of object A when it's 4 meters away from object B. That's actually... okay, now I have to think a little bit again. Because that's not t... my first thought was put t equals 4 into both and just subtract them. Alright, it is CU. Well, listen, the first bit... Hey, we're picking up some marks, right? The first bit's not too bad. Okay, so... Let's get into this. So... I want to figure out when the objects are away from each other. Okay, so I want to determine the position of object A when it's 4 meters away from object B for the first time. In other words, I want to figure out the difference between the position of object A and the position of object B. Okay, so I know a few things. I don't know the time at which this occurs. Do I care about the time? So the position of object A when it's 4 meters away from object B for the first time. I'm just care about position. Maybe I might need t to sub it at some point, but for now, I know that the change in position, if I have RA with respect to t minus... Wait, did I use little r's before? Capital R's? I can't write capital R. What is capital R? Oh, whatever. I feel like little r is position. I don't know why I've done capital R's. I can't even write capital R. I've had that problem writing the letter R all day. Alright, R, B, T. Okay, whatever. I've used capitals. No point changing it now. Let's commit to using capitals. So, I know this is going to equal 4, right? If I take the magnitude between these two vectors, I'm going to get a answer of 4. So, I think the logical step is to take the magnitude of two vectors and see what I get, know it equals 4, and use that to solve. Like that kind of what makes sense to me. So if I substitute each of my vectors into this idea, I'm going to wind up with the absolute value of... These vectors are both so long. Can I just column vector them? Is that gonna make things any better? Do you know what I'm gonna do? Because if I take the magnitude of my vector, then it's going to be the square root of my I coefficient squared plus my j coefficient squared. Let's just find our I coefficients and our j coefficients first. So before I actually worry about this, I'm simply just going to find, before I put my magnitude stuff in, I'm going to find RAT minus RBT. Okay, I'm just going to subtract these two. And I'm going to write them ambitiously as column vectors, because I just think it's going to be maybe faster. So it's going to be minus 2 cosine 3t. That's my I coefficient. Sorry about all the swiping back and forth. 2 sine 3t plus 2. Okay. 2 sine 3t. And it's just 2. Just plus 2k, right? Plus 2k? Minus 2k. Plus 2. Plus 2k. Okay. That's the first bit done. So now I want to do the same thing with the second part. It is going to be sine t cosine t minus 1. So it's minus sine t cosine t minus 1. I want to subtract all of these to get my new position vectors. Oh, they're all going to kind of suck a little bit, aren't they? Alright, so do I write them back in terms of I, J, and K? I guess I can. It might be easier, I feel like, for people watching if it's in terms of I, J, and K when I find the modulus. I'm going to do that, but we can subtract them a bit easier like this. So I'm going to wind up with minus 2 cosine 3t minus sine t, and I can use some big brackets here. Everything is inside a bracket. That's my I coefficient. I'm now going to plus, using brackets, 2 sine 3t minus cosine t j. And my k's at least are kind of nice. It's literally 2 plus 1. So it's just going to become 3k. That part's kind of nice. So now I want to take the magnitude of all of this, which means I take my I coefficient squared plus my j coefficient squared plus my k coefficient squared. So if I do that, and I'm square rooting all of it too, just to make it even better. If I'm doing all of that, then the magnitude of RAT minus RBT is going to be equal to the square root, I'm not going to have enough space, I'm going to have to write small, of minus 2 cosine 3t minus sine t, all squared, okay. Ooh, still don't have a lot of space, plus 2 sine 3t minus cosine t squared. Well, actually, it's just 3 squared. I'm just going to write that as plus 9. Okay. You kind of squeeze it all in there into one line. I'm going to have to bracket expansion all this. It's not too bad. It's just, gosh, there's a lot here. There is a lot here. I can get rid of my square roots. Okay, I can. I've had that realization that it's going to be easy to get rid of the square root. I'm just going to... I know this equals 4, okay? I know this equals 4. I did it up here. I'm going to use that substitution right now, and I'm going to square both sides and make it 16, if we're following, right? I can get rid of the square root, make things look a little bit neater. I know that this equals 4. If I square 4, I get 16. So basically, I'm going to square this side, and I'm going to square this side. If I square both sides, we're balancing. I can get rid of the square root. I know the magnitude of RA minus T, RAT minus RBT equals 4. If I square 4, I get 16. Okay, hopefully you're following where those numbers come from. That is equal to, I can now do my expansion. That is going to equal, well, that's just going to become 4 cosine 3t. So I should say cosine squared 3t. Multiply my two terms together. I get plus 2 sine t cosine 3t, and I double it. So that's going to become plus 4 sine t cosine 3t in the middle, and then I square the last term. I'm going to wind up with plus sine squared t. Wow, that is just the first bracket. I've almost used all the space. I'm going to put my second expansion below. So now I'm going to do the same thing. Whatever, it's fine. I'm going to do the same thing. I'm going to wind up with square the first term. I'm going to get 4 sine squared 3t. Then I'm going to become, again, multiply the two terms together, double the product, however you want to do your perfect square expansion. That is going to become minus 4 cosine t sine 3t. I'm just lining up my angles. I don't know why I'm doing it that way. It just happens. I could have done sine 3t, cosine t, it's fine too. Plus sine squared t, and then I'm just going to write plus 9. I should put a little plus here. Plus 9. Well, I just figured may as well layer it since we're layering it. I'm just going to put the 9 here. I changed my mind. It just looks too silly to have a 9 all by itself. That can go back there. And it's all meant to be one big line. It's just like, wow, it's just one gigantically big line. So hopefully some of us can start to spot that we have a bunch of trig identities occurring here. That's kind of why I, in some ways, lining up the angles might hopefully make a few things pop out to people. I really need my formula sheet to remind me of every single different identity I could use. Okay. Okay. I've said okay a few times in a row. Oh! I messed up something here. This is meant to be cosine. Alright. That's why I was like, oh, I don't have another cosine. I do have another cosine. Sine squared plus cosine squared equals 1. I don't think I said that right. Sine squared plus cosine squared equals 1. So that's going to equal 1. Okay. That is going to equal 1. So that part's equal to 1. That's great. And I've got 4 cosine squared plus, 4 sine squared. That's going to equal 4. So I can do the same thing over here. And that's going to equal 4. So I can get rid of some of these terms here. Okay. Which is nice. I can get rid of that. Now, I'm just going to rewrite that actually. I'm going to make things a little bit easier. I'm going to write that out. That is 16 is equal to 4 plus 1 is going to give 5. I may as well make this a 5 if I combine my two highlighted bits. 5 plus 4 sine t cosine 3t minus 4 cosine t sine 3t. What am I doing? I have to add 9 in. I'm going to add 9 in as well. If I add 9 to this, might get 16? Oh, wait. No, I'm a fool. I'm a fool. I had 16 on the brain. It's 9 plus 5 is 14. Yeah, 14. Okay. So I get to this. Oh, I didn't realize I was blocking that. It was just the 16 that was blocked. So I think the rest of it should have been able to be followed. I can now consider... One of my rules I have is sine of A minus B. Sorry, is equal to sine A cosine B, right? So... I kind of got this situation occurring twice. I don't know why my brackets are so messy. Let me fix up this bracket here. I've got this situation occurring twice in both of these scenarios. I have a slightly different rule for the second one. Oh, sorry, I missed half of this rule. Apologies. Let me fix in the second bit. That is going to be cosine A sine B. Okay, so that's my rule. From the formula sheet, bam, got my rule. Happy-ish days. Happy-ish days. So I can now apply that to what I have above. I've got, literally this whole thing, I've got sine times cosine, cosine times sine. And the angles are the same, and I guess I could use a different color here to kind of show angles are the same. So, I can turn this into sine A minus B, and I'm going to wind up with, I said this was going to be straightforward, it really wasn't. I'm going to wind up with 16 is equal to 14. I guess I could subtract 14 and get 2 straight away, but we don't need to go and do that just yet. Equals 14. That's going to simply become plus... Well, I've got a 4 out the front, so it's supposed to have a 4 at the front of everything. It's going to become plus 4. It's going to become plus 4 sine of... It is simply going to be... Well, I guess in this case, it is t minus 3t, so it's sine to the negative 2t. Right? Yeah? Yeah. Sine to the negative 2t. Okay. So, I can now, pretty confidently, I would say, I can subtract 14 from each side. Yeah, I can subtract 14 from each side. I'm going to wind up with 2 equal to... I guess I can make this a half. I can divide, sorry. I can subtract 14 off each side, then I can divide both sides by 4. I'll write that out. That is 2 equal to 4 sine. I can actually do a little trick here. I make this positive. If we remember, a sine, like sine negative theta equals sine theta, I can basically take the negative just out of any bracket. If it's a sine function specifically, I can just take the negative out and I'm happy. If it's cosine, the whole thing becomes a negative. I can still bring the minus sign out the front, but in sine, I can just disappear it. Nice little magic trick. I can divide both sides by 4, and I wind up with this here. I'm running out of space. It says end of paper. There it is. We're so close to the end. Do I get a spare page? I do get a spare page. So, write which question number you're responding to. Question 19. There we go. I'm following all the rules. So, I wind up with sine 2t equals a half. And if I start to consider my absolute value options, okay, basically 2t is going to be equal to sine of pi on 3? Pi on 6. Pi on 6 is going to give a value of a half, and I can divide both sides by 2, right? I'm going to wind up with, I guess I have multiple solutions. Is there a boundary condition in this at all? There's no boundary conditions. I mean, I've got infinite options for my value for t, where the two particles could be, I guess what I'm trying to find, to make this clear, I'm trying to find the time when they were 4 units apart. If I find the time when they're 4 units apart, I can put that into my equation to figure out the position of particle A at that time, and that basically answers the question for me. If I consider other solutions, I've got pi on 6 is one of the options, and, well, it's going to be 5 pi on 6 is my other option, right? They're going to be two situations or positions where I get that kind of result. Yeah, I'm sweet. Everything's fine. I got rid of the negative. Everything's fine. Or did I need the negative? I think I'm cool. I'm just gonna keep swimming, right? So I get t equals pi on 12. If I consider 5 pi on 6 as the other solution, where I'm basically quadrant 1, quadrant 2, right? The other solution, there's also like technically 5 pi on 12 could be a possible time as well, right? As these things kind of go around the cycles. It's sinusoidal, so there's going to be many times where the distance will be 4 between these two particles or objects, or however we want to phrase them. So, hang on, pause. Wait. Okay. Let me fix this, because I got it the wrong way around. It happens to the best of us. Sometimes we're filming late at night, and we swap our sine and cosine rules around. This needs to be, we need to readdress this. Because it's led me the wrong way around. I can get rid of the negative inside the brackets, but what I said happens with cosine when the negative comes out the front, that is sine. Right? That is sine. So I need to take my negative at the front of my sine function, like so, because cosine's in quadrant 4. I made it very simple. But mistake I shouldn't make, so apologies. The negative comes out the front. I actually get a negative half over here, and that means now my solutions are in negative quadrants for cosine, for sine, which is going to be quadrants 3 and quadrants 4. In quadrants 3, it is simply just going to be, 7 pi on 6, and in quadrant 4, which I probably don't need quadrant 4, but just to include it for the sake of including it, just kind of like we did before, that is going to be all the way around to 11 pi on 6, which means I get 2 possible options for time, which is going to be 7 pi on 12 and 11 pi on 12. I can now find, I'm just going to use the first positive solution, because why not? There was no domain given, so like I said, they're cyclical. There's going to be many times where the two particles are going to have a distance of 4. We just want to find the first time, which, for the first time, there we go. We want to find the first time, which, when I said the first time, that triggered, I'm pretty sure I read that, so there we go. So I want to find the first one. So me considering the second solution is a not necessary thing to do for this question, I can simply now just find my position A. We did it, 7 over 12. That is going to equal, where's my position vector for A? That is going to simply equal -2 cosine of, oh my god, it's 3. It's 3, isn't it? It is 3t, which means that simplifies out, and I get 7 pi on 4. Wait, I don't even need t, because that is t. 7 pi on 4. May as well put my I part in. Sorry for all the swiping back and forth. then it's 2 sine 3t plus 2. So this is going to become plus 2 sine of 7 pi on 4 as well. That's my j component, plus 2k. That part is going to be unchanged. And I wind up with... Whew, we did it. We did it. I wind up with an answer of minus 2 multiplied by... It's going to be in quadrant 4, which is great for us because cosine's positive. So I simply wind up with minus 2 multiplied by root 2 over 2. That is simply just going to give negative root 2. I'm going to wind up with, minus, in this case, because sine in quadrant 4 is going to be negative, minus sine of, it's going to be the exact same situation, which is going to become minus root 2j. Sorry, I've got my I part there, and I'll bring this a little bit closer so we can see, and it's going to become plus 2k, and that is my answer for the position. I guess it's meters away, right? That is my answer for the position of my, I'll zoom in more so it doesn't go all faded. That is the answer for my position of the two particles when A is 4 meters away from B for the first time. All right, we did it. We actually got to the end. And, you know, there was times there where we had to do a lot of thinking. And when I'm trying to talk and explain, sometimes my thinking goes in the back burner. So apologies for the malfunction I had around this. But if you guys subscribe and you watch my videos, you'll find that is very rare and almost never happens. So please subscribe to the channel. That would really help me out a lot. I'm going to be posting more exam content. So if you need help with anything, specialist or methods, all that content is going to be coming, and hopefully I'll see you guys in the next video. Have a fantastic rest of your day or night. Goodbye, everyone. Peace out. Why did I say peace out? I'll have to fix that. I'm just going to say goodbye, everyone. I'll work on an outro. You know, we'll figure all these little things out as we go. But everyone, I hope you guys found the video helpful. Feel free to comment down below anything you feel like you would like to see, and I'll try to make sure I get some content out on that for you guys. Goodbye.